online lecture series. Welcome student, welcome to the online lecture series of Sri Chhatrapati Shivaji Maharaj College of Engineering, Nepti. Our today's subject is microprocessor, and the topic of today's lecture is debugging. Debugging is nothing but a single step exception or breakpoint exceptions that allows you to check the errors in your programs. The 80386 also uh, supports the debugging feature, but the mechanism of debugging is changed. That is, in 80386 it supports debug registers. The debug registers are supports both instruction breakpoints and data breakpoints. The data breakpoints are important innovation that can save hours of debugging time by pinpointing, and the breakpoint registers eliminates the complexity associated with writing a breakpoint instruction into code segment. So these are the contents of our lectures, that is debugging features of architecture, debug register and debug exception. So we will start with debugging feature of architecture. This feature of 80386 architecture that supports debugging include reserve debug interrupt vector that permits processor to automatically invoke a debug task or procedure when an event occur that is of interest to the debugger. Then 4 debug address registers. This permits programmer to specify up to 4 addresses that the CPU can automatically monitor. Then debug control register. This allows programmer to selectively enable various debug conditions associated with the 4 debug address that we have seen previously. Then debug status register. It helps the debugger identify condition that cause the debug exception. Then trap bit of TSS, that is T bit. It permits monitoring of task switches. Then resume flag, RF flag or flag register. This flag allows an instruction to be restarted after a debug exception without immediately causing another debug exception, immediately causing another debug register exception due to the same condition. Then single step flag, that is TF flag or flag register. This flag allows complete monitoring of program flow by specifying whether the CPU should cause a debug exception with the execution of every instruction. Then breakpoint instruction. This permits debugger intervention at any point in program execution and debugging of debugger program. Then next is a debugging feature. These features make it possible to invoke a debugger that is either a separate task or a procedure in contents of current task. The debugger can be invoked under any of the following conditions, that is first, task switch to a specific task, execution of breakpoint instruction, then third, execution of every instruction, then fourth, execution of any instruction at a given address, then attempt to change the debug register. The this feature also provides read or write of byte, word or double word at any specified address, or write to a byte, word or double word at any specified address. Then next is a debug register. There are total 8 registers are available, that is DR0 to DR7, but DR4 and DR5 are reserved by Intels. So only DR0, DR1, DR2, DR3, DR6 and DR7 registers are available for debugging. These 6 registers are used to control debug features. These registers are accessed by MOV move instructions. A debug registers may be either the source operand or destination operand. The debug registers are privileged resource. An attempt to read or write the debug registers when executing at any other privilege level cause a general protection exception. This figure shows the format of debug register. Then debug address registers DR0 to DR3. These 4 debug registers provides the address of debug register. Each of these registers contains the linear address associated with one of the 4 breakpoint conditions. Each breakpoint condition is further defined by bits in debug register 7, that is DR7 register. The debug address registers are effective whether or not paging is enabled. The address in these registers are linear address. If paging is enabled, the linear address are translated into physical address by processor's paging mechanism. If paging is not enabled, these linear address are same as physical address. As you know this concept in our chapter number 5. When paging is enabled, different tasks may have different linear to physical address mappings. Then next is debug control register, that is DR7 register. For each address in registers DR0 and DR3, that is debug address registers, the corresponding fields read write 0, the corresponding fields read write 0 through read write 3 specify the type of action that should cause a breakpoint. The processor interprets these bits as follows. For 00, it will interpret as a break on instruction execution only. For 01, break on data writes only. For 10, it undefined. 11, break on data reads or write but not instruction fetches. Then next is for len0 and to len3, that is length 0 to length 3. This specifies the length of data item to be monitored. A length of 1 or 2 or 4 bytes may be specified as shown in PPT. For 00, it will specify 1 byte length. For 01, it will specify 2 byte length. For 10, it will specify 3 byte length address, and for 11, it will specify 4 byte address length. Then these are the bits of debug control registers DR7 registers, that is G0 to G3 bits, L0 to L3 bits, G bit and LE bit. Let's see. The low order 8 bits of DR7, that is L0 to L3 and G0 to G3, selectively enable the 4 address breakpoint conditions that is specified in debug address registers. There are 2 levels of enabling: the local, that is L0 through L3, and the global, that is G0 to G3 levels. The local enable bits are automatically reset by processor at every task switch to avoid unwanted breakpoint condition in the new task. The global enable bits are not reset by any task switch, therefore they can be used for a condition that are global to all the tasks. The LE and GE bit, that is exact data bits, local exact and global exact bits. If either LE or GE is set, the processor slows execution so that the data breakpoints are reported on the instruction that caused them. It is recommended that one of these bits must be set whenever data breakpoints are comes into action. The processor clears LE bit at a task switch but does not clear GE, that is global exact bit. Then next is a debug status register, that is DR6 registers. So these are some bits B0 to B3 bits, BT bit, BS bit and BD bit that are used for debugging purpose in debug status register DR6 register. When the processor detects an enable debug exception, it sets the low order bits of this register, that is B0 to B3, before entering the debug exception handler. The BT bit is associated with the T bit, that is trap bit of the TSS. The processor sets the BT bit before entering the debug handler if the task switch has occurred and the T bit of the new TSS is set. There is no corresponding bit in DR7 that enables and disables this trap. The T bit of the TSS is sole enabling bit. The BS bit is associated with the TF, that is trap bit of flag register bit. The BS bit is set if the debug handler is entered due to occurrence of single step execution. The single step trap is highest priority debug exception. Therefore, when BS is set, any of the debug status bit may also be set. The BD bit. This bit is set if the next instruction will read or write one of the 8 debug register. The next, debug exception. Interrupt 1 debug exception and interrupt 3 breakpoint exception. The two of the interrupt vectors of 80386 are reserved for exception that relate to debugging. Interrupt 1 is a primary mean of invoking and interrupt 3 is intended for debuggers and for compatibility with previous processors in Intel's family. First, interrupt 1, that is debug exception. The handler for this exception is usually a debugger or a part of debugging system. The processor causes interrupt 1 for any several condition. The debugger can check flag in DR6 and DR7 registers to determine what condition occurred the exception and what other condition might be in effect at the same time. This table shows with each breakpoint condition the combination of bits that indicate when that condition has caused the debug exception. Instruction address breakpoint conditions are fault while other debug conditions are traps. The debug exception may report either or both at one time. Here in this table it will shows the BS bit to 1. It will cause the condition that is single step trap debug occur. The next B01 and G0 or LE0, that is global exact 0 or local exact 0 is equal to 1. At that time the breakpoint DR0 means the DR0 register's address will be selected and the length is selected, length 0 and read write 0 is selected. Also for B1 is equal to 1, B2 is equal to 1, B3 is equal to 1. The similarly G1, G2, G3 is selected and these flags are set. Because of this flag set, the corresponding breakpoints address DR1, DR2, DR3 are select for the debug address. The next BD is equal to 1. This causes the condition debug registers not available in use by ICE 386. Then BT is equal to 1. This causes the condition of task switch. Then next is a interrupt 1 debug exception. These are some points: instruction address breakpoint, data address breakpoint, general detect fault, single trap, single step trap, task switch breakpoint. Let's see one by one. First, instruction address breakpoint. The processor reports an instruction address breakpoint before it executes the instruction. This begins at any given address. That is, if an instruction address breakpoint exception fault occurs, the RF, that is restart flag bit, permits the debugger handler to retry instruction that cause other kind of fault in addition to debug fault. When it detects a fault, the processor automatically sets RF in the flag image that pushes onto the stack. Whenever RF is set, it causes any debug fault to be ignored during the next instruction. The processor automatically clears RF flag at the successful completion of every instruction except after the IRET instruction. Also, processor automatically sets RF flag in the E flag register on the stack before entry into any fault handler. Then next, data address breakpoint. A data address breakpoint exception is a trap. That is, the processor reports a data address breakpoint after executing the instruction that access the given memory item. When using data breakpoint, it is recommended that either the local exact or global exact bit of TR7 registers be also set. If either local exact or global exact is set, that is LE or GE is set, any data breakpoint trap is reported exactly after completion of the instruction that access the specified memory item. This exact reporting is accomplished by forcing the 80386 execution unit to wait for completion of data operand transfer before beginning execution of the next instruction. If G or LE is set, data breakpoint may not be reported until one instruction after the data is accessed, or may not be reported at all. Then next, general detect fault. This exception occurs when an attempt is made to use the debug register at the same time. This additional protection feature is provided to guarantee that ICE 386 can have full control over the debug register. Then next, single step trap. This debug condition occurs at the end of the instruction if the trap flag of the flag register held the value 1 at the beginning of that instruction. The processor clears the TF bit before invoking the handler. If TF is equal to 1 in the flag register of TSS at the time of task switch, the exception occurs after the first instruction is executed in new task. The single step flag is normally not cleared by privilege changes inside the task. The INT instruction, however, do clear trap flag. Therefore, software debuggers that single step code must recognize and emulate INT-N or INT-O rather than execute them directly. The next, task switch breakpoint. The debug exception also occurs after switch to the 80386 task. If the T bit of new TSS is set, the exception occurs after control has passed to the new task, but before the first instruction of that task is executed, the exception handler can detect this condition by examining the BT bit of the debug status register, that is TR6 register. Then next is interrupt 3 breakpoint exception, INT3 instruction and breakpoint exception. This exception is occur because of by execution of the breakpoint instruction, that is INT3 instruction. Typically, a debugger prepares a breakpoint by substituting the opcode of 1 byte breakpoint instruction in place of first opcode byte of the instruction to be trapped. When execution of INT3 instruction causes the exception handler to be invoked, this saves the value of pointer that points to the byte following the INT3 instruction. With prior generations of processors before 80386, this feature is used extensively for trapping execution of specific instruction. But with the 80386, the needs formerly filled by these features are more conveniently solved via the debug registers and interrupt 1. However, the breakpoint exception is still useful for debuggers because of the breakpoint exceptions can vector the different exception handler than that used by the debugger. The breakpoint exception can also be useful when it is necessary to set greater number of breakpoints that permitted by the debug registers. So this will ends our second topic, that is debugging from unit 5. Thank you.